first. Okay. And if you're ready, let's get started.
Okay. Hello, everyone. My name is Gyeonghun, and I am currently a master's student at DISL at KAIST. Today, I'll present our paper RAQE, Reranker-Aligned Query Expansion via Label-Free Group Relative Policy Optimization. So at the moment, the paper is under review for COLM. So before getting into the method itself, let me briefly start from RAG, since the paper is about improving retrieval inside a retrieval augmented generation pipeline. So most of you are already familiar with RAG, but just to frame the discussion, the basic idea is that given a user query, the system first retrieves relevant documents or passages from external corpus, and then those retrieved pieces of evidence are given to the language model to help it generate a better answer. So the pipeline is usually query, then retrieval, and evidence, then generation. Now, the important point here is that the retrieval step is often a bottleneck. Even if the generation is strong, if retrieval fails to bring back the right evidence, the final answer quality will still be limited. And this is exactly where query expansion comes in. So two main problems in user queries are first, lexical mismatch, which is relevant documents may use different wording than the query. And second, query under specification. So user queries are often too short or too ambiguous. Because of this, the original query may not be expressive enough for the retrieval to find the best evidence. So query expansion tries to solve this by augmenting the original query with additional contextual information. So the big picture is if we want better RAG, we often need better retrieval first. And if you want better retrieval, improving the query itself is one natural direction. So recent LLM-based query expansion work has mainly developed along two directions. The first direction is training-free methods. Examples include hide and query to doc, Muji, and word to passage. These methods use LLM to generate pseudo passages from the original query and then combine them to the generated text with the query for retrieval. This is attractive because it doesn't require any training or human relevance labels. In other words, you can just use it immediately. But there's a downside because many of these methods improve performance by increasing the generation budget, by generating multiple pseudo passages, or by scaling up the generator. That often means repeated generation at inference time, which increases latency quite a lot. So they suffer from high inference cost. And the second direction is RL-based query expansion. Examples include LLM-QE and OBQE. These methods train a model so that at test time, it can generate a single strong expansion in one pass. But they define the reward using retrieval metrics that depend on human relevance annotation, such as NDCG based on query document labels. That means they require large-scale human-labeled relevance data during training. And in many real deployment settings, especially in new or cold start domains, that kind of supervision is expensive or unavailable. So this creates a practical trade-off. So on one side, if you want to avoid supervision, existing methods are often slow at inference. And on the other side, if you want efficient single-pass inference, existing RL methods typically require costly human labels. So RAQE tried to answer this trade-off question, which is, can we train a single-pass query expansion model without relying on human relevance labels? And RAQE answers that by replacing human labels with a Reranker-derived proxy reward. So RAQE tries to build a query expansion model that is both label-free during training and single-pass during inference. So to do this, you use a Reranker as a source of proxy supervision. Instead of asking humans to say which documents are relevant to each query, the method uses cross-inquiry Reranker scores as a substitute signal for relevance. These scores are then transformed into a reward that can guide policy optimization. So you formulate query expansions as a relative decision problem, which is the goal is not to estimate some absolute relevance score perfectly, but to learn which expansion is better relative to other expansions for the same query. So for the framework, it has three ingredients. The first is re-ranker scores are used to construct a proxy reward. And second, the model is trained in a distilled and optimized manner. In other words, it's not trained with RL from scratch. It first learns to produce reasonable pseudo passages through SFT, and then it is further optimized with policy optimization. And the policy optimization algorithm is GRPO, which works naturally with relative preferences among a group of candidate expansions. So the intuition is use distillation to teach the model to form good expansions, and then use re-ranker-based preference signals to align those expansions with retrieval effectiveness. So this figure shows the two-stage training pipeline and the inference behavior. RAQE trains a policy model that generates a single concise pseudo-passage given a query. And this pseudo-passage is concatenated with the original query to form the expanded query. The training happens in two stages. So stage one, the model is warm started using supervised fine-tuning. A strong teacher LLM model generates pseudo-passages for sample training queries, and then the student model is trained to imitate the teacher outputs. This stage teaches the model to generate concise and well-formed query expansions, which makes later all optimization easier. In the second stage, the model starts from that distilled checkpoint and is further optimized using GRPO. So for each query, the method constructs multiple candidate expansions and retrieves top K documents for each expanded query and scores those documents with a cross-encoder re-ranker and computes an RSDG-based reward and then updates the policy to prefer the candidates with higher rewards. And the important point here is that all of this only exists during training, and at inference time, the model doesn't call the re-ranker and does not generate multiple candidates iteratively. So it only simply generates one pseudo passage, and that's why the method is low latency. So to summarize, stage one teaches the model how to write expansions, and stage two teaches it which expansions are better for retrieval. So the central contribution of the paper is the reward called RSDG, which stands for Reranker Shaped Discounted Gain. The easiest way to understand RSDG is to view it as a label-free approximation of NDCG. So in standard NDCG, we need human labels to say which documents are relevant and how relevant they are, but our goal is to avoid using those labels during training. So instead of human labels, we use cross-encoder re-ranker scores as proxy for relevance. So for the definition, first, given an expanded query Q prime, the retriever returns the top K documents. And then for the each retrieved document, D prime I, we compute a re-ranker-based gain, which is on the notation S, Q, and D prime I. So here, it is the cross-encoder re-ranker score, which is CE in the notation. And we clamp the negative values to 0, which is that DCG style gains should be non-negative, so it makes it more stable for the optimization. And then the next notation is for the RSDG. The numerator is a DCG style score over the retriever's ranking for the expanded query Q prime. So if the retriever puts high gain documents near the top, the value becomes larger. And the denominator is the ideal discounted gain computed by sorting these same retrieved documents according to the Reranker scores. So this plays the role of IDCG and standard IDCG. The important choice here is that the Reranker score is computed with the original query queue, not the expanded query queue prime. So if we use the expanded query in the Reranker, then the model would reward for documents that simply match the generated expansion text itself. And in that case, the model could exploit the reward by generating text that is easy to match rather than the text that truly helps the user's original information need. So by using the original query queue, we keep the relevant signals anchored to what the user actually asked for. So conceptually, RSDG asks the following question: that does this expansion help the retriever produce a ranking that agrees more with the Reranker's preference ordering while still being grounded in the original query? So the RSDG use it in two places. First, to filter useful distillation examples in stage 1, and second, to define the reward for policy optimization in stage 2. So this is stage 1 in a bit more detail. The stage provides a strongest enunciation for policy model. So directly optimizing RSDG from scratch would be difficult because the retrieval-based rewards are non-smooth and depend on discrete rankings. So instead of starting RL from scratch, we have the stage 1 for SFT training. For the data, we use 5 benchmark datasets: NF Corpus, FIQA, Fever, HotPotQA, and MS Marco. So from each dataset, sample 3,000 training queries, and then a teacher LLM, Llama 3.17 billion instruct, generates a pseudo passage for each query. So each query and pseudo passage pair becomes a candidate supervision example. But not every query or teacher generated passage are useful, because some might sound fluent but actually hurt retrieval. So we apply a filtering step based on retrieval impact. So specifically, compute the improvement in RSDG between the expanded query and the original query, and then only keep the examples where the improvement is positive. And after filtering, only about 6,000 training queries in total across those 5 datasets are left. So the key for stage 1 is the model learns the language and structure for good pseudo passages, but only from examples that appear to be helping retrieval. And stage 2 is GRPO using RSDG. So the setup here is that we use a fixed offline rollout groups rather than fully offline exploration. So for each training query, we prepare a group of candidate expansions. So in our main setting, we use the group size 8. So each candidate, we recompute both the retrieval results and the re-ranker scores. So this makes this avoids the expansiveness of training process and also makes optimization more stable. So for each candidate expansion EI, we form the expanded query Q prime I. So I compute the RSDG score and then compare it to the original query. So the reward is like the following: RI. So this reward directly measures how much the expansion improves retrieval over the original query. If an expansion helps, the reward is positive, and if it hurts retrieval, the reward becomes smaller or negative. Then within each rollout group, we standardize the rewards to compute the group relative advantage, which is the A hat I. So we're not trying to learn a globally collaborated absolute reward scale. Instead, for each query, we want the model to learn which candidate expansion is better relative to the others in the same group. So the optimization focuses on within query preference ordering. This is why GRPO fits the problem quite naturally. The policy is then updated using standard GRPO objective, which is the following. And here the rho I is the likelihood ratio between the current policy and the reference policy. So this objective increases the probability of candidate expansions with positive relative advantage while keeping the updated policy close to the distillized initialization. So overall, stage 2 takes the worms started expansion model from stage 1 and makes it explicitly retrieval aligned using relative preference learning while still keeping the training procedural practical. So this is the brief experimental setting. So the paper evaluates RAQE on 2 levels. First, retrieval quality, and second, downstream tech performance. So for retrieval, we use two retrievers, BM25 for sparse retrieval and contriever for dense retrieval. The main metric is NDCG at 10 with human relevance tables at evaluation time. So they retrieved the top 10 documents for evaluation. And we used 8 data sets in total. So 5 are in-domain data sets that are used in the training. And then the 3 are out-of-domain data sets used to test generalization, which is Arguana and Q and SciDocs. For the backbone model, use the Llama family generators with 8B and 3 billion, trained with LoRa fine-tuning. So the experiments are designed not only to show gains on the training distribution, but also to test whether it generalizes over other retrieval settings and datasets. So this is the main results. So the important point is that RAQE consistently improves retrieval quality across both sparse and dense retrieval. So this table is for the sparse retrieval. And this is from the BM25 results and with the RAQE with 8 billion generator, which is on the bottom line and achieves the best NTG at 10 among methods using the same backbone size. And in several datasets, it's also competitive with or better than 70 billion prompting baselines. So, for example, RAQE reaches 36.0 on NF corpus and 84.5 on FIFA and so on. And there's also a dense version of this table, which is on the appendix of the slides. It's not here on this page, but it shows a similar result. So RAQE works both well on sparse and dense retrieval compared to the LLM-based prior work. And this one is quality latency trade-off. So the retrieval quality against latency as the backbone size scales from 3 billion to 70 billion. And the key result is that RAQE achieves strong retrieval improvement with only a modest increase in latency, while repeated generation methods such as hide, Muji, and word to passage incur much larger latency overheads. So the message is not that RAQE is the absolute fastest method overall, but the message is that it offers very favorable balance on single pass inference like efficient methods, but retrieval gains closer to or better than much more expensive methods. So simply scaling the generator is not enough, and alignment with retrieval objective matters more for converting model capacity into actual retrieval gains. And this part is reward validation. So we use RSDG, but we have to see if the proxy reward is actually reflecting well in line with the original NDCG. So first, we look at pairwise agreement for pairs of candidate expansions to RSDG and human-ended CG prefer the same one. And then next, we also report Spearman and Pearson correlations over the full rollout group. So the table shows 0.73 for pairwise, which is quite higher than random chance, which is near 0.5. And the correlations in the other ones are also reasonably positive. So the reward itself is not perfect by alone, but it seems reliable enough to induce meaningful preference ordering among candidate expansions. And these are other evaluations for ablation and reward ranker choice. So we try to show that both stage 1 and 2 are effective. So the line on the top is no training at all, and then the second line is only stage 1, and the third line is only stage 2. And the last one is our method, which uses both stage 1 and stage 2, and you can see that our method is constantly scoring high among all. And for the ranker choice, because reward might depend on ranker choices, so we try to show that on like other rankers, it doesn't like go down for retriever scores. So we can use other rankers, and thus RSDG score is not dependent on the ranker model itself. So this is for beyond retrieval metrics and whether these improvements matter for downstream tasks such as generation. So evaluate on 2 downstream settings, which is open domain question answering for NQ and fact verification on fever. So in both cases, they use PM25, top 5 retrieval, and feeded them into chunks into the Llama 3.1 70 billion instruct for generation or verification. So the tables show the comparison with the original methods with LLM-based generation. So among those, our method still show the highest among metrics like EM, F1, and accuracy, and macro F1. So to conclude, RAQE proposes a practical middle ground in query expansion. The paper addresses a real trade-off in prior work, which is training-free methods avoid human labels but are often slow at inference, while RL-based methods are efficient at inference but depend on expensive human relevance supervision. So RAQE tries to resolve this by introducing 3 key ideas, which is a label-free ranker-based reward called RSDG, and a distilled and optimized training strategy, and a single-pass query expansion at inference time. Across 8 retrieval benchmarks, as well as downstream QA and fact verification tests, the method shows consistent gains. And that's all for my presentation. Thank you.
Okay, so thanks for the nice presentation, which was very clear and covered most of the part in the original papers. So for my case, I already know the details about the paper, so want to give more chance to the student or other people joining in the session for the QA. So welcome any questions from the audience.
I have a question. Thank you for your presentation. I think there is a part I didn't understand very well. I think at the beginning you had the slide where you show that this slide, maybe number 6. Yeah, this is slide. So you are using a smaller model to generate these extensions of the queries, and then you identify which extensions are better for retrieval using this re-ranking, right? Later I understood that for the ranking, you are using the original query, not the augmented query. So
Yes.
I wonder how are you able to identify which extensions are better if you are using the original query in all cases?
Oh,
I'm
okay.
not sure I
So,
understand.
oh yeah, that part might be confusing. So we make the expansion from the original query and then
Mm,
make the expansion with adding the original query to the expansion. So we search, we retrieve the top key documents with this expanded query. But then if we compute the similarity between the expanded query and the documents retrieved, then the model might not catch the original intent of the user because like if it just expands wrong, weird contents and it just retrieves a weird also document, then it will just score high and not get
okay.
the original query. So we get the original user's intent and then score the similarity between the document and the original query. So that's
Okay,
the reason.
okay. I understand. Perfect.
Yeah, so to summarize, the retrievals was done with the expanded query, but the computation of similarity for the cross-encoded score is between the retrieved chunk and then the original query.
Okay, thank you.
Okay, any other questions? Okay, then no question from student side. So let me ask some questions regarding the limitations you have in mind. So do you think of any limitations on your method? Because you're the main author of the paper, so maybe you clearly understand what downside the method have.
Well, actually, one of the downside is it would have been better if we had better retrieval scores over than the um, LMQE or OPQE, which is use the RL-based method. We can only, for now, say that we are more efficient and we don't use the labels, but I know that it is hard to overcome the methods that use the actual NDCG for training, but still um, not able to, the situation not able to show improvement in the retrieval scores are quite um, not satisfying. And one other one would be that we use the offline RL method. Well, it would have been better if we could show that online method is also workable, but in our setting, we only could use the offline setup. So that would have been one limitation. Also.
Mm. So the first limitation is the comparison with the method, RL-based method with the human NDCG scores, right? But some part of the values in the tables showing that your method achieves the even higher scores over the strong baseline, such as the LLM-QE. So do you have any thought on the improvement over the strong baseline, even with the approximated the relevance score?
Yeah, I'm happy and satisfied with that
Yeah.
result, but yeah, it might have been better if we just could didn't have to put the like upper bound title for LMQE and just compare it together.
Yeah. Maybe some reviewer might ask like that. You mentioned the LMQ as upper bound, but your method shows the score even higher value than the upper bound. So the naming of upper bound quite misleading. Yeah, so that is one point. And also, lastly, what kinds of future research agenda or topics can you think, can you come up with based on this starting research? So if you keep continuing the similar line of work like this one.
So I guess the formulation of RSDG is quite, what should I say? The idea is quite not very difficult in the sense of math or stuff like that. So it's a kind of a new idea. So I think there is a point to make improvement in the reward itself. And as I mentioned, it can use online. If there is a better reward that is not too sparse, then we can try online RL, which can improve more on retrieval scores. So I think I can make the efficiency and also the retrieval accuracy higher than what the RAQE has right now.
Yeah, that's one good direction. And also I can think two possible directions. The first one is integrating your proposed I forgot the exact name. What? How do I spell it? RSDG? Yeah, maybe. Yeah.
Nice.
Yeah, RSDG scores, you can integrate the score in the pipeline of the agentic RAG. In the agentic RAG, there are multiple components like query expansion and retrieval multiple times by creating the subqueries that the model cannot retrieve the evidence at the moment. Like there is some more complicated chain of the component in the agentic RAG. So maybe you can utilize your score as a proxy word similarly what you done here in that another field. And the second one is the detailed study to see that your methodology can be generalized against more challenging queries or domains like if I look at all the data set you experimented in the main table, most of the data set have only short form answer, probably, right? So it is quite questionable if your work can perform well, still well, across the data set that need long form generated responses from the model. So anyway, yeah, that's just the two ideas I have. Yeah. Anyway, other questions? If there is no question, let's wrap up today's session here. Okay. Thank you so much, everyone. Have a great day.